Dear President, officers, and members of the Geochemical Society, dear colleagues, it's a great honor to be the 2021 Goldschmidt medalist. It's humbling to look over the list of past recipients. Many of them are my science heroes and were a source of inspiration. I can trace my interest in the geochemistry of volatile elements to when I was just 6. I saw a documentary, Les Rendez-vous du Diable. The presenter, Arun Taziev, was a unique blend of adventurer, scientist, writers, movie maker, and excellent communicator. One of his mantras was that the key to understanding active volcanoes lies in the gas phase, and noble gas are pure physical traces, which fitted very well my physics background. So I wrote to Professor Ozima at the University of Tokyo, one of the leading scientists in the field, who kindly responded that I was welcome. My colleague and friend Yuji Sanos and a PhD student developed there the analysis of helium in volcanic gas of Japan, and I became interested in the relationship between noble gas and major volatiles. Helium-3 was particularly interesting because it's the only isotope for which a mantle flux is quite well known thanks to oceanic studies. Helium in morb glasses sampled several high-temperature volcanic gas along the Japanese arc with my motorbike, and I found that the carbon-helium-3 ratio in morb is near constant, but that of arc gas is on average 1 order of magnitude higher than in morbs, evidencing the contribution of the slab to arc magmatism. Combining flux estimates from noble gas with this new relationship led me to quantify the exchange rate of carbon between solid Earth and the surface, and these estimates are still in use in global carbon cycle studies. When I returned to France, I obtained a junior research position at the CNRS in Paris. A professorship position later on opened at the CRPG, Centre de Recherche Pétrographique et Géochimique in Nancy, when Francis Albaret moved to Lyon. There, a group of young scientists, Marc Chaussillon, Etienne Deloul, Christian Francelanor, Guy Bourrel, Laurie Resberg, and later on Pete Bernard, were eager to explore new areas of research with enthusiasm and new instruments. I built a nitrogen noble gas system, and with Laurent Zimmermann and Nicolas Dauphas, we characterized the nitrogen isotope composition of the convective mantle and the plume mantle respectively. Turning to cosmochemistry, we developed a technique for grain-by-grain analysis of lunar soil with Rainer Willer from ETH Zurich and Koa Shizume, then postdoc. We were approached by Don Burnett, PI of the NASA Genesis mission that sampled the solar wind Lyon over 3 years, and the nitrogen isotope composition of the Sun was one of the 2 major objectives. So we worked very hard for 6 years to decrease the nitrogen blank of the line to do the experiment. With Marc Chaussillon, we duplicated the analysis with the large sector ion probe installed at CRPG, and both methods led us to conclude that nitrogen of the solar nebula is 40% poor in nitrogen-15, thus giving us a key to better understand stable isotope variation in solar systems. With my student and postdoc, among them Reika Yokochi, Michael Broadley, Evelyn Fury, Laurette Piani, David Byrne, Mathieu Almerac, and others, we found that neon trapped in the deep mantle is solar, presumably resulting from dissolution of a nebula-like atmosphere, that heavy noble gas in the deep mantle are chondritic, in agreement with stable isotope pointing to an inner solar system origin for terrestrial volatiles. With Yves Marocchi, Maya Kuga, David Becker, and Lucille Pentecost-Quinet, we carried out ionization experiment aimed at reproducing the isotope pattern of primitive organic matter found in meteorites by ionizing gas mixture. This experiment gave us strong support for photon-gas interaction as the main source of organic matter in the solar system. From noble gas data obtained during the ESA Rosetta mission studying comet Churyumov-Gerasimenko, we proposed that comets contributed about 20% atmospheric noble gas, but negligible amount of water, carbon, and nitrogen, thus resolving the long-standing problem of the origin of the ocean. Altogether, these studies highlighted the many sources of volatile elements that contributed to the building of an habitable world. More recently, we have been investigating the composition of the ancient atmosphere and ocean by looking at paleoatmospheric gas trapped in fluid inclusion in Archean hydrothermal quartz. With Pascal Philippot from IPGP, Ray Burgess from Manchester University, Magali Pujol and Guillaume Avis, then both PhD students, We found that during the Aldean and Archean, atmospheric xenon evolved isotopically from a cosmochemical member composition to the modern one. This evolution was a result of X plus escape to space, providing a tool to investigate interaction between the ancient Sun and the Earth's paleoatmosphere, as well as to trace the chemical evolution of the atmosphere through deep time. In closing, I would like to express my sincere thanks to the many colleagues I have had the privilege to interact with throughout my career, in particular researcher, engineer, postdoc and student at CRPG Nancy, who have made it such a great place to work. I have a special thought for Pete Bernard, who left us too soon, and I wish to thank Annie, Louise and Edwige for bringing me personal balance in a life busy with science. Again, thank you very much, and now enjoy the Goldschmidt conference. Thank you.